Okay, systems, excuse me, systems of equations. This is what chapter 3 is all about, is systems. We're going to solve them graphically and algebraically both. Systems are very important. You have one equation that describes one situation, another equation describes another situation. Where do those two equations have a solution that is shared? That could be your optimal situation. We're actually going to do something near the end of this chapter called linear programming, where you have a bunch of parameters, equations showing different parameters. Using those parameters, what's your best solution? What's your best possible outcome? This is a form of system of equations. One of the times I used systems an awful lot, particularly was in college in my physics class, because you have a system. An object is moving. There's a system. There's a bunch of equations that describe the motion of that object. You got something sliding down a ramp, and you have all these equations to describe that motion, and you're trying to find out particular things. I remember one in particular was you've got a string wrapped around a dresser and you're pulling on it. At what point does it tip over rather than slide? Okay, it's a complicated thing, except for I have the equation that describes this, and the equation that describes this, and the equation that describes this, and the equation that describes this. As long as the number of variables and the number of equations were the same, or I had more equations than variables, if there was a solution, I could find the solution. So that's what I had to figure out. I had to figure out which equations could I use, which ones did I need, did I have enough variables involved to be able to solve the system. Because it wasn't one equation, plug in the numbers, and you get your answer. You had several equations and several different variables you had to work with. And I knew as long as the number of variables was at least the same size as the number of equations, the number of equations was at least the same size as the number of variables, I was okay. If I have 2 variables, I need 2 equations. I've got 3 variables, I need 3 equations. And we will work with systems with 3 equations in here. Okay. Linear system means that all the equations are linear, and you can have linear equations that have more than 2 variables. Okay, 3 variables is a straight line in 3-dimensional space, if you wish to graph it that way. But I've worked with the linear systems that have 4 or 5 or 6 variables. What makes them linear is each variable has no exponent, no root, no nothing. It's just x, y, z, nothing other than how many of those we have. Minus 2x plus 3y, 4z equals 5. As long as there's no powers or anything, it's a linear equation. And you can have 5 or 6 or 7 or 8 variables with linear equations. You can't graph them, but they are still considered linear equations. Solution, and this is the important concept, is the values that make all of the equations true. It's the one place, the one set of values that make all of them true. Okay? Consistent system has at least one solution. Inconsistent has no solution. Graphically speaking, if we're working just with 2 straight lines, an inconsistent is where I have 2 parallel lines that don't cross each other. They're parallel lines, they don't cross, there's no solution. There are 2 types of inconsistent. I don't really care about separating them for your answers, but there are 2 types. There's one where you have, the most common one, where you have 2 lines crossed, you get 1 point, you get 1 answer. The other one is the 2 equations are versions of each other. If you graph them, you get the same line, which means they have an infinite number of solutions because it's the same line for both of them. Every point that works in one works in the other. Okay. Now we're going to start by doing them by graphing. Graphing is probably the worst way to solve a system. You have to be really, really awesome at graphing to get a good solution by graphing. But what it does do is provide a picture of what we're talking about. That's all you get from graphing, from solving by graphing, is it gives you a visual picture. So I'm going to graph the first line in red. My y-intercept is 5, 1, 2, 3, 4, 5. My slope is -3, so I go over 1 and down 3. And that is the first line. Graph the second one in green. My y-intercept, let x equal 0. My y-intercept is -2. Let y be 0. My x-intercept is 4. There's my two lines. This is my solution. Where they cross. It's the only place they have in common. That's the solution to the system. This red line represents the infinite number of points that's a solution to the first equation. There's an infinite number of xy coordinates that will make this true. That's what the red line represents. The green line represents all the xy coordinates that work in this equation. There is one that they have in common. That one point is what shares in those two systems. Okay? Now, I'm not asking you at this time to find that solution, because graphing really sucks, particularly when you're using a big fatty marker and not a ruler like I have here. Okay?
No packing on the corner.
But the question is this consistent or inconsistent? Do I have a solution? Yes, so this would be a consistent system. If I do the same thing on the next one, y equals 2. X equals -4. This is consistent, and my solution's easy to get on this one. It's the point -4, 2. Because x is -4, y is 2, always. So this one is consistent. Same thing, a couple more examples, I think. Yeah. So once again, graph the first one. 2x minus y equals 7. So the y-intercept is -7. The x-intercept, 7/2, which is 3.5. 1, 2, 3.5. My y-intercept is -3. My x-intercept is 9/6. 9/6, which reduces down to 3/2, right? Yeah. Which is 1.5. Well, interesting. Do I have a solution? Does not appear that I do, does it? Doesn't appear that I do. I haven't graphed them. Doesn't appear that I do. However, it's easy to tell. If I look, these appear to be parallel lines, which means that it would be inconsistent. Inconceivable, right? Okay, last one. Graph the top line. Y-intercept is 2. My slope is 1/5. So I go over 5. 1, 2, 3, 4, 5, and down 1. And there's that. Graph the second line. My y-intercept is 5. 1, 2. Sorry, my y-intercept is 2. Ooh, same one. My x-intercept is -10. Is that right? I messed up somewhere. Where did I mess up? You're right. I did a negative slope. You're right. I did. I screwed that one up. My bad. Not on my game this morning. 2, 2, 3, 4, 5, 1. There you go. And 2. And this is really lousy because it's supposed to be over here for my y-intercept. But if I look at it, if I were to rearrange this one, I would get y equals 1/5 x plus 2, which is what? The same line. So this is consistent. And technically, I have an infinite number of solutions. This is one of the ones where graphing it really doesn't go well. If I had used a ruler, it would have helped, right? Okay, and there are ways to graph straight lines that are better than this. I really don't care. But this one is consistent because technically it has an infinite number of solutions. Because technically they are the same one. Questions so far? Okay, your turn. Do those two. Okay, so we do the first one. If I let x be 0, y-intercept is -3, and the x-intercept is, if I let y be 0, I get -1. For the second line, my y-intercept is +1. My x-intercept is -1. And they do cross. They have a shared point, so this is consistent. That shared point on this one is relatively easy to find because I have the most x-intercept, so it would be -1, 0. You should strive to identify the solution from graphing. Like I said, it is the worst way of solving systems of equations. This graphing, you want to do it algebraically. That's the better method for doing it, but this is doable in a pinch. I like it more to give a picture of things rather than anything else. Same thing on the next one. My x-intercept is -2. My y-intercept is +1. That's the top equation. My y-intercept is 1. My slope is 1/2 over 2 up 1. And oh, looky. It is a consistent system. Technically, with an infinite number of solutions, all the shared points because they're the same one. Okay, so this one is a little different. You want to do the same thing, only you want to do it without graphing. Now, here's the easy way, because I'm only asked 2 things. I'm asked if it's consistent or inconsistent. First step, compare the slopes. It's the easy way to do this. Okay, first step, you compare the slopes. So, I don't have either one of them in slope-intercept form. Very easy to do with this one. Take the top one, rearrange it by adding 3x to both sides. Y equals 3x plus 4. If I take the top one, and I want to rearrange it to put it y equals mx plus b4, first thing I would do is subtract x from both sides. So that would give me -1/3 y equals -x plus 1. And then I want to get rid of the -1/3, so I want y by itself. So what do? Multiply everything by -3. So that gives me y equals 3x minus 3. Okay. So the question is this consistent or inconsistent? What kind of lines are these two lines? They're parallel lines. They have the same slope and do not have, the slopes are the same, but the y-intercepts are different. These are parallel lines. Slopes are the same, y-intercepts are different. It is inconsistent because they are parallel lines. You remember parallel lines? Good old geometry days, parallel. Same thing on the next one. Okay. Kind of. I can very easily do the same thing on the next one. And I want to see if they're parallel lines or not parallel lines. Are the slopes the same? The slopes not the same. Okay. But if I look at this one, if I look at the second one in particular, I have 2x and 4x. If I can make them the same equation, make the x's and y's the same, I can tell whether or not this is parallel. Roll with me on this one. This one's a little different. Roll with me on this one. Take the top equation, multiply everything times 2, and write it right underneath the bottom equation. So do the top equation times 2, everything, and write it underneath this one. 4x plus 6y equals negative 6. Yeah. Not 6y, 2y. My bad. Thank you. Knew I was doing something wrong. 2y. Sorry, my bad. Is it 6y? It was 6y. Okay. Equals 12. Okay, so I screwed up. I knew I screwed up. Plus 6y equals 12. Thank you. I knew I screwed up somewhere. Sorry, not on my game this morning. Are my x's and y's both exactly the same? No, then these are not parallel lines. They're not the same line. They will cross each other. If my x's and y's are not the same, if it's in standard form, and my x's and y's are not the same, then it's consistent. They will cross at some point. They're not parallel lines. It's not the same line. It will not happen. These two lines will cross. This is a consistent system. Okay. Because the lines will cross each other. Okay. X's and Y's are not the same. I won't have the same slope. Okay. The slope of the first does not equal the slope of the second. The slopes are different. They cross each other. You're done. You know you have a solution because they won't cross each other. Slopes are the same. They might still be consistent. And I think that's what we have in the second one. So the top equation is already in mx plus b form. If I take the bottom equation, make it in mx plus b form. First step, subtract 6x from both sides. Negative 3y equals negative 6x plus 9. Divide everything by negative 3. Negative y equals 2x minus 3. So I have 2x minus 3 and 2x minus 3. Slopes are the same. Y-intercepts are the same. It's the same line. This would be consistent. And technically, it has an infinite number of solutions. and it's the same line. Okay. It is consistent because it's the same line, it's the same equation. If I graph this line and if I graph this equation, graph that equation, I get the same line. Same thing, just rearranged to look differently, that's all. Okay. Your turn, do those. Okay, so consistent or inconsistent by analyzing it by graphing. First one, I've got one equation in y equals. So it's just easiest to change the second one into y equals to make it match. So I add 4x to both sides. So I get 2y equals 4x minus 4, divide everything by 2, and I get y equals 2x minus 2. I get this, I get that. It is consistent because there are two versions of the same line. Second one, kind of the same thing. I already have one equation in y equals mx plus b form. Rearrange the other one to make it mx plus b form. It's the easiest. So I subtract 2x from both sides. Gives me negative 2y equals negative 2x plus 5. Divide everything by negative 2. Y equals x minus 5 halves. I have this one, and I have that one. And this would be inconsistent because I have two parallel lines. Slopes are same, y-intercepts are different. They're parallel lines. This one would be inconsistent. And then on the last one, I can look at it right now and tell that they're not going to be parallel lines. They're not going to be the same line. Easiest way to do this one, I can either rearrange, or I can do what I did on the other one, try to make them look the same on x's and y's. If I multiply the bottom one times 3, I get 3x plus 12y equals 15, and the top one is 3x minus y equals 2. Those are not the same equations. They do not have the same slopes. To have the same slopes, the x's and the y's would be the same. Okay, two parallel lines in standard form, x's and y's are the same, but the number on the other side is different. These lines cross each other. This is consistent. Okay, questions? Okay.